Week 18, lesson 1. Guys, you have made it to the last week of new lessons. Week 18 is your last little bit of sort of calculus introduction. Next week will be the final exam. So it'll be like in little pieces throughout the entire week. But anyway, let's talk about week 18, lesson 1. So we're talking about rates of change here. So if you read this first example, there is an equation right here. Okay, and this is the position function, meaning when I plug in x values, which are times, right? So x could be 1 second, 5 seconds, 8 seconds, whatever. I'll be solving for y, and that will tell me the height of this billiard ball. Okay, so it's a position. Depending on what I plug in for x, I will know the height of the billiard ball. So here for question A, when it's asking for the average rate of change over this interval, these are both x values, and I'm going to plug them both in. Okay, I'm going to plug in x equals 1. I'm also going to plug in x equals 2. So I will figure out that at second number 1, when I plug this in, I get negative 16 plus 100, that the ball is 84 feet up. Okay, and when I plug in 2, let's see, negative 64 plus 100, I get y equals 36, okay, which makes sense, right? It says that the ball is dropped from a particular height. After 1 second, you can see where the ball is, and after 2 seconds, you can see where the ball is. And it makes sense that those heights are lower because of gravity. Okay, now I have not actually answered the question. The question here is the average rate of change. Okay, so that would mean, like, if you had this as a picture, right, this ball's being dropped and it's going to kind of look like a parabola. At 1 second, you're at this particular height, right, and at 2 seconds, you're at a lower height. The average rate of change is the slope of this secant line. So literally, all I have to do is figure out the slope, the change of y over the change of x. Okay, so if you'll look right here, I have two y values. So I'm going to find how much they have changed. All right, and then the change of x would be over here. Again, you have to make sure you're just doing it in the same direction. So 1 minus 2. And if you subtract, you'll get 48 over negative 1 or negative 48. All right, that's the average rate of change. That's about how much the height has changed within that 1 second. Okay, now, as you're looking down here, notice that it's asking slightly different question, okay? This question is asking for instantaneous rates of change, okay? Instantaneous is dependent on the derivative. Okay, so let me find that derivative, all right? I believe I get negative 32x. Okay, so instantaneous rates of change, right, at the endpoints of the interval, I still have to plug in 1 and I still have to plug in 2, but this time I'm plugging into the derivative. Okay, so when I plug in 1, I get negative 32, and when I plug in 2, I get negative 64. Now, what should seem sort of interesting, or at least it's interesting to me, is that if I add these up and divide by 2, I do get the average rate of change. Okay, so now let's take a look at the next page. Okay, so as I'm looking at this next example, we've got a silver dollar. It's being dropped from the top of a building, and they give us the height of that building. And then it says that there is a function here, s sub t, and then all this other stuff. So what you need to know about this particular function is that v sub 0 here is the initial velocity. Initial velocity. All right, and s sub 0 is the initial height. Okay, so this is where things are starting and what its starting speed is, all right? Now, the good thing about this particular example is that the initial velocity is going to be 0 because it's just being dropped from the top of the building. If it was being thrown down from the top of the building, you would have an initial velocity. Okay, so the position function is going to be this one that you're seeing up here, but with some numbers plugged in. So S of t is equal to, let's see, I have negative 16t squared. The initial velocity is 0, so I don't have this middle term. And then the initial height was given over here, so it's 1362. Now, this position function I can use at various times, right? If I plug in t, and I will figure out various heights. Right? If I plug in 1, I will know where that silver dollar is at 1 second. If I plug in 2, I'll know where the silver dollar is at 2 seconds. Now the velocity function is the derivative of the position function. So let me take this derivative. I get negative 32t. And this one down below, if I plug in t equals 1, I'll know how fast the silver dollar is going. If I plug in 2, I'll know how fast the silver dollar is going. Okay, so the top one is all about height and time, and the bottom one is about speed and time, or velocity and time. Okay, this comes in really, really handy, and it's really, really important for the rest of these questions because you're going to need to know which of these functions am I using. Do I care about position or do I care about speed? Okay, so on question B, it says the average velocity. This is a lot like the first example we did at the very beginning of this particular lesson, which means I need to plug in t equals 1 along with t equals 2 into the S function, because this is going to tell me the heights, right? When I plug in 1 into the S function, I will get a height of 1, 3, 4, 6. And when I plug 2 into that position function, I will get a height of, let's see, negative 16 times 4, 1362, 1298. Okay, now I know this may seem weird because I just said that the position function tells you about height. But we want an average velocity, right? Now think about this. Velocity is, for example, feet per second, right? That's what velocity is, it's feet per second. So I want to know what the change of feet is in a certain amount of seconds. Okay, so that's exactly what I have here. I have a change of 1346 minus 1298 over this change of time, 1 minus 2, excuse me, I get negative 48 on the top, and, no, I'm lying, I get positive 48 on the top. I get negative 1 on the bottom. So it's negative 48 feet per second, which hopefully makes sense, right? It's just, we know what the height was at a certain time. We know another height at a different time. This is the average rate of change. Now for part C, because it's asking for instantaneous velocity, I'm going to use the V function, the velocity function, when the time is 1, along with when the time is 2. Okay, so plugging in here, negative 32 times 1, I have negative 32 feet per second. And when the velocity is 2, negative 32 times 2 is negative 64 feet per second. Okay, on question D, the time required, right, so I will be solving for t, for the coin to reach the ground, okay? When the coin reaches the ground, the height is 0. So when I use the S function, this part is going to equal 0. Negative 16t squared plus 1362, which means I'm going to move this to that side and get 16t squared equals 1362. Dividing by 16, t squared equals 85.125. And if I take the square root, we get, actually it's not equals, it's more of an approximate 9.22 seconds. Double check me please, but I'm pretty sure that's right. Okay, so next, looking here, it says find the velocity, which means I'm going to use the velocity function of the coin on impact. Okay, that means I need to use what I got in the last answer. This is when the coin is on the ground. But here I want to know how fast was it going instantaneously when that happened. Okay, so the velocity function of 9.22 is negative 32 times 9.22, which is approximately 295.24 feet per second. Okay, next, the question is how high is the coin when it's going, oh sorry, wrong thing, let's move that up, there we go. How high is the coin when it is going negative 64 feet per second? Okay, so I already have a velocity, so I'm going to plug this into the velocity function. So negative 64 is the velocity. The question is telling me when I do this, it's going to tell me the time. Is that going to tell me the height? It is not. Okay, all I know is that at 2 seconds, it's going the correct velocity. Now let me go back to the position function and plug in that t value of 2. So when I plug that in, I get negative 16 times 4 plus 1362, which gives me a height of 1,298 feet.